Michel was born in 1956 in France, and I can tell you that he is a runaway engineer. He ran away from the engineering courses. He was admitted to the most prestigious French colleges, which is known as École, Grande École, and he was doing electronics engineering, and he was in the second year. In the third year, he simply left the course, and he spent several years in the famous village Aroville in Pondicherry, and 20 years he has lived in Nilgiris, and he did the English translation of Mother's Agenda, which is 13 volumes, and India's Rebirth and India the Mother, from French to English. So that was a tremendous amount of work. I can tell you that he is a walking compendium in Indian civilization and culture. Probably I have not seen people that much knowledgeable and aware of our old heritage, and he has at fingertips vast amounts of information and knowledge. So his love for Indian civilization and culture is phenomenal, and he has authored the first book that is very well known is The Invasion That Never Was, published in 2000. This is related to Aryan invasion because he debunked this theory of Aryan invasion. And then the second is The Lost River on the Trails of Saraswati. It was published in 2010 by Penguin. It is one of the most kind of acclaimed books now on Saraswati River. And Indian Culture and India's Future was published more recently in 2011, and he is now working on the dawn of Indian civilization and elusive Aryans. This is to be published soon, I hope. He has lectured and toured any number of educational and cultural institutions all over the India. He has been to Roorkee also earlier, and he has lectured at many of the IITs and IIMs and universities. And right now he is a guest professor at IIT Gandhinagar, where he is located since 2011, and he spends almost half year there probably, and he is establishing or helping in establishing a center for archaeological sciences there. It will be a very scientific center with all the equipments and everything. And he has been a member of the CBSE course Committee on Knowledge, Traditions and Practices of India, and he has already contributed to the textbooks for class 11th and 12th with Professor Kapil Kapoor. And there are several of his works that are included there. I can also mention that he is now a member of the this Indian Council of History, ICHR, and he is also a member of the Executive Committee of the Banaras Hindu University Executive Council, Banaras Hindu University, and he spearheads many other committees and programs. And how he managed to do that is really amazing, and I am really privileged that he is here among us today to lecture on this topic, with which he is well versed, and he has made original contributions in this area. So with these words, I request Michel to please come on the stage and give his lecture.
Namaste, and my gratitude to Ashokji, first of all, the Sanskrit Club, secondly, and all the administration, supporting administration of IIT Roorkee, and all of you for coming to this talk. It's a great pleasure to be back at IIT Roorkee after perhaps some 7 years or something like that. And there is something very enjoyable about this place and this institute in particular. Yesterday I had an interaction with some of these young members of the Sanskrit club, and it was also very enjoyable. And there is a dynamism here which I hope will, crystallize into many attempts and projects which can inspire other institutions and universities in the country. In fact, I chose this topic, first of all, because this is something that we all wonder about. You know that in the national press, you will find all kinds of controversial articles about how much did the ancient Indians really know about science. Did we have vimanas? Were we able to transplant heads, of animals onto people's bodies and things like that? So there's a lot of confusion and, let us say, low level of information, which is also used in turn to ridicule the field. So you have both extremes. Those who say we had everything, from vimanas and nuclear weapons to relativity and quantum physics, and those who say, on the other hand, that we had nothing and let us stop boasting about this. So this is a surprising situation. Surprising because the amount of scholarly work, scholarly means very solid, academic, rigorous, non-controversial work which has been done on Indian science is phenomenal. It began in something like I think it is 1818, by Henry Colebrook, British Indologist, who published for the first time the algebra of Brahmagupta and Bhaskaracharya in translation, 1818. And then after this, it all grew and grew, and Indian scholars joined, and especially in the 20th century, we have had a monumental series of publications on all these works of great Indian scholars, some of whom you are seeing on this map, only a few of whom, very few of whom. Why exactly do we have controversies about something? It is as if having controversies about, I don't know, computer science. There is no controversy. You can just go to the material and look it up. The problem has been that this field, for a number of reasons which I will not go into, it would take too much time, has been eclipsed in our educational system. And as students at school level, at college level, at university level, you have not been exposed to this field of history of science. A number of reasons. One of which perhaps I should mention, and it is essentially a lack of self-confidence. That we do not feel confident about our legitimate heritage, and we are talking here about an intellectual heritage in particular. We do not feel confident about it, and we are always waiting for others to come and document it. So, in fact, the only film, I was having a talk with Professor P.K. Ghosh yesterday, the only good film that I'm aware of on history of Indian science and technology was made by the BBC, not by, our Indian channels. So we have still a long way to go to reclaim, this ownership and this feeling of legitimate pride. I do not mean a hollow pride, I mean a pride founded on legitimate knowledge. We still have a long way to go. But nevertheless, there have been a number of attempts, and there is certainly a growing interest in the country, and I'm confident, optimistic, that within the next few years, we'll have a wide range of genuine material on this field of science and technology in ancient India. By genuine, I mean material which is non-controversial, based on very solid material. Now, once in a while, of course, a controversial question may come up, and I will highlight a few of them here today, because we do not have yet answers to all the questions that arise from the field. And you will see why very shortly. But this is now an ongoing effort, and I think that the national mood is in favor of doing justice to this field. So let me begin by, first of all, apologizing for dropping the word technology from the title, because when I was preparing this lecture, I realized that it is just too huge. Let me concentrate rather on a few very important issues which would give you a qualitative understanding of the field rather than a quantitative understanding, which you can inquire. Actually, even now I am giving a course of some 18 lectures at IIT Gandhinagar as purely an introduction to history of science and technology, and it is even that in 18 hours is just still a very, very superficial introduction. So I cannot pretend to do much more in 1 hour. Now what you see on this map is which incidentally is adapted from a website which has a huge amount of data on Indian mathematicians and astronomers, and that website is St Andrew University's website in Scotland. We do not have a single university, or IIT for that matter, having any amount of material on this field. So I redrew their map differently to show you, and I am not going to read it out, you've had it in front of you for some time, where some of the leading figures of especially the classical period, which we call the Siddhantic period, after the word Siddhanta, which in this special meaning means a treatise, a set of conclusions, a set of principles. So a treatise. So this happens starting with Aryabhatta, who was working at Kusumapura, as he tells us, which has been identified with Pataliputra and therefore somewhere near Patna. And this is really the beginning of the classical period, but there were antecedents, some of which I will very briefly spend a couple of minutes upon. So you see that there is something happening. After this, you will have Varahamihira, you will have Bhaskara the first, Bhaskara the second. Before that, you have Brahmagupta. And you have really an effervescence and a hugely creative period where these people not only create, but they comment upon each other. And this is actually the very important part which I want to insist upon today, that this tradition is an intellectual tradition. Just as you've had in ancient India intellectual traditions on philosophy, on grammar, language, on all aspects of knowledge, basically. All these are knowledge traditions. In science, you see, for example, there's one manuscript appearing in Kashmir in the 8th century, and within 50 years, you have a commentary on that manuscript within 50 years somewhere in South India. So these channels are wide open. They function very well. There is no internet, and yet you find that these manuscripts circulate very well. I suppose riding piggyback on the pilgrimage networks. This is my own assumption. And you know, scholars travel with manuscripts and they keep exchanging and meeting. So it's a very lively tradition which at some point gets disrupted. We know historically, and we have direct testimony from Al-Biruni in the 11th century, that the major disruption is, of course, the political instability brought into North India by the Islamic invasion starting from the 11th century. And therefore, you see a movement southward and ultimately the last stage, efflorescence of this great intellectual tradition happens in Kerala from the 14th to the 17th century, and that you would have heard about in greater detail from Professor Ramasubramaniam when he visited you last time. Now, before we get into the heart of the topic, one crucial question is this: how much do we know? How much do we really, can we really estimate of what was actually achieved? Can we say that we are covering this field, you know, to a satisfactory extent? Now, we can take as one element of answer the study done in 2002 by a very great scholar of history of science and technology. There were many of them in the second half of the 20th century. He was Professor K.V. Sharma, who passed away a few years later. And he, in fact, was very familiar with the South Indian manuscripts of science and technology, and he himself published a number of them, especially from Kerala. And he surveyed 400 collections of manuscripts still located in libraries, universities, private collections, institutes of Tamil Nadu and Kerala. And he found there 3,473 science texts, which were repeated over a number of manuscripts. But then he found that out of these, only 7% had been published. So 93% of these scientific texts still waiting for us, waiting for some scholar to come and sit and decipher the script, because they are all in various scripts of various epochs of Tamil Nadu and Kerala, and therefore it requires great skill for scholars to read them and collate them and compare the various manuscripts and so on. No more than 7% has been published. So 93% we just do not know. We do not know what is there. Some of it may be repetitive, some of it may be of inferior quality, but nevertheless there will be a lot of very precious material which we simply are ignorant of. And this is what K.V. Sharma said, that we are judging as if the whole and soul of the contribution is this 7%. This is a sorry situation from which Indian science has to be rescued and resurrected. But we have a long way to go, because our mass of epigraphists and manuscriptologists is diminishing day by day. There are fewer and fewer people going into the field. So to take one example, Aryabhatiya, you see, is the main work of Aryabhatta. And I'll very briefly give you one or two points from it. But he published another work. He wrote another work, which is Arya Siddhanta. And that is not available. It is lost. There are many texts which are lost, and they are often available only through fragments found in later commentaries. There is a whole tradition of commentaries where Aryabhatta, for example, writes very, very briefly in an extremely concise and often obscure language, 131 verses. The entire Aryabhatiya can be printed in 7 or 8 pages. So after this, you have 13 commentaries in the whole of India commenting upon it and explaining. And if we didn't have them, it would be very difficult for us even today to understand what he's really trying to say. So through that, we can reconstitute part of Arya Siddhanta, but the text is lost, except that perhaps it is still waiting for us in some of these manuscript collections. Now, I start at the Rig Veda. You have all heard about Vedic mathematics, but Vedic mathematics, which is a set of valuable techniques of fast calculation, is not properly speaking Vedic. It is a recent reconstruction. It is not found in the Vedas. And in the Veda, you do not find that much of mathematics, if I mean really the Vedic Samhitas, the hymns. But you do find a few important clues to what's going to happen later. And possibly this is the most important of all, where you find that in the Rig Veda, this is a very ordinary hymn. There is nothing very special about this hymn. It is a hymn invoking Indra and asking Indra to come to us with 2, 4, 6, 8, 10 horses, and then 20, 30, 40, all the way to 100 horses. And of course, it's a symbolic language. Rig Veda is highly metaphorical. What exactly it is trying to say, I will not go into, it's not my purpose today. But this is important because India, and you know this much, and we will come to it a little later, India created the decimal-based numeral system, which the whole world is using today, and which did not, without it, no modern science would be possible. Now we can see here one of the antecedents of it, and how the Sanskrit language in particular is favoring this multiplicity of these multiples of 10. In fact, the Rig Veda itself goes to 1 lakh. And Yajur Veda, which is a slightly later Veda, concentrating on the ritual aspect of the Vedic religion, goes up to a Parardha, and that is 1 million millions. So this is another feature here, which will be a second ingredient of the decimal notation of numbers. And it is a search for large numbers. There's a kind of obsession starting here and developing to an incredible degree later on in Buddhist texts like this one, Jain texts also, where for some reason, they are trying to work out, so, you know, lakhs and crores and lakhs of crores and crores of crores, and they will be giving names to all of these higher multiples, and you see here some you cannot see, of course, it's too small, but these are names in Sanskrit of 10 to the power 43. Every multiple of 10 has a name or several names. And it goes on to 10 to the power of 145. All of them have a name. Whereas, if you compare to Greek mathematics, in Greek mathematics, the highest named number was 10,000. It was the myriad. You know, myriad is a term which has passed into common English, but in ancient Greek, it meant 10,000. That's all. Beyond this, there was no name. And even namelessly, they will be reeling out, for example, the young Buddha in the Lalita Vistara Sutra is interviewed by a guru about his knowledge of mathematics, and he starts reeling out all these colossal multiples of multiples of multiples, and it goes on to a number equivalent to 10 to the power of 421. Now, you might ask, what is the use? Immediately, no use at all. Immediately, no use at all. You can't use these numbers for anything. But the great use will be conceptual. It accustoms the mind to think in terms of multiples of 10 on a very wide scale, and this is what will actually help create this decimal-based numeral notation, which will be India's major contribution in mathematics. We move on in time, and we come to the 6th century BC or so, where we have the Shulba Sutras. Now, the Shulba Sutras are texts of geometry to construct Vedic altars. Very simple, plain altars made of bricks with 5 layers of 200 bricks each in various shapes, circular, square, shapes of tortoise, that will be the Kurmachitti, shapes of falcon, the Shenachitti, and I cannot spend time explaining how it all works, but here, very interestingly, and the altar is nothing but a miniature representation of the whole cosmos. The bottom layer is the earth, the highest layer is the highest heaven, and in between you have intermediary worlds. So you are offering a sacrifice to the cosmos, symbolized by this altar, but for some reason, they will be imposing mathematical rules. For example, each altar has a fixed area, and you are allowed to change the shape of the altar. The fixed area is 7.5 square purusha, the purusha being this much, a man with extended arm upward. So this is 7.5 square purushas is the area of the altar. And you have to total it up with bricks which are of any particular shape. They may be rectangular, they may be triangular, they may be trapezoid, semi-trapezoid, and so on. So you have to calculate the area of each brick, add it up, and make sure that 200 of your bricks come up to the imposed area. And whether you have a circle, whether you have a square, whether you have a falcon, the total must be the same. So this will lead to lots of geometrical constructions, which I will not go into, but which will lead to a lot of very pioneering results, one of which is this, and this is an exact quotation from Bodhayana Shulba Sutra, which is the main of the 4. There are 4 surviving Shulba Sutras, and where he tells you, because they will be constantly transforming a figure into another. So how to geometrically construct a square which is the sum of 2 squares, how to geometrically transform a square into a rectangle or vice versa of same area, how to geometrically transform a square into a circle and vice versa, which actually is not geometrically, can never be a perfect procedure. It can only be approximate, and so on. And these will lead to numbers of results. this is one of them, and I think you can recognize what we are talking about here. This is obviously the Indian expression of what goes by the name of Pythagoras' theorem. And except that it is expressed not by a square plus b square equals c square, but purely in a geometrical form. But it is exactly the same. And the expression is perfect. So you see, this is one problem that we have in our educational system, that I don't mind if it is called Pythagoras' theorem. Let it be called this or that, it doesn't matter. But why can't we, when we teach it to our children, why can't we just mention, at least in passing, that this theorem also figures in the Shulva Sutras, which are probably earlier. They are dated 6th to 8th century BC. Pythagoras was 5th to 6th century BC. In any case, Pythagoras did not leave any work. It is in Euclid, 300 BC, that the theorem is first expressed and attributed to Pythagoras. So anyway, it's not a matter of claiming that we are first or no. My point is, we should at least say that, well, it was also worked out independently in India and in its full form, but in a geometric expression. And it's troubling that we do not take the effort. We do not make the effort of at least teaching these small tidbits. Then in the Shulva Sutras, and here you can see the beginning of a new tradition, which is the tradition of metrology. Metrology is the science of measuring things, measuring lengths, measuring surfaces, measuring volumes, measuring time also. So all these dimensions will require units, and you can see some of them, which I will not explain further, but then you can see how this is the beginning of the classical Indian dimensions, which common Indian people are sometimes still using even now, despite decades of metric system. You know, I don't know in North India, but in South India, if you buy a length of jasmine, mala, it will be measured with this, which is the cubit. And this cubit is here. It is the aratni or hasta. In fact, hasta will become hat in Hindi later on. So this is an important tradition because it will be adopted by people at large. And they will be using these traditions not only for linear units, but for units of weight in particular. And it has been proved now that the traditional weight system, which was still in use in Indian markets shortly after independence, until the metric system finally replaced it, and some of our elders here would remember it, this weight system actually originated from the Harappan civilization. It was the same weight system that Harappans were using. So you can see the survival of certain tradition over millennia. Now, I have been speaking about this decimal system. What exactly are we talking about? This is an inscription, possibly one of the first, but there are other inscriptions which have been claiming to be earlier, where you see some king in Gujarat writing 3, 4, 6 in a local era, and that means 346. Now, you may take it as absolutely obvious, but there's nothing obvious about it. Romans, for example, the Roman Empire, were using Roman numbers which you are somewhat familiar with, which are totally different. If you are to write 346, you'll have to write a C, and then 40 will be I and V, and the 6 will be something else. And it will be all non-positional in the sense you cannot make direct additions, you cannot make direct sums. It will be very complicated to do any mathematical operation with non-positional numbers. So what is here unique is not exactly the positionality, that is to say each digit 3, 4, 6, because of its position means something different. It's a multiple of hundreds, it's a multiple of tens. That was something the Chinese had already worked out. Even the Mesopotamians, long before, who had a system of numerals in base 60, not in base 10. The Mesopotamians also had a positional system, but neither the Mesopotamians nor the Chinese were able to do one critical last step, which was the integration of the 0 as a mathematically significant number. If it had been 3, not 6, you would have a 0 here. This was beyond the Mesopotamians or Chinese. Why? We take it as absolutely obvious today. There's nothing obvious at all. 0 is nothing. So how do you use nothing? This requires a high level of conceptualization, abstraction, and this last step was made only in India. And this was the major contribution. So people say India invented the 0, it's wrong, it's not correct. The Mesopotamians had a symbol for 0 as a placeholder, because sometimes they knew that there was nothing, and they would just put a symbol. They had one cuneiform symbol for 0. The Mayans also had a 0, but none of them could turn it into a mathematically significant number and work out the rules. You know that 0 multiplied by another digit is 0. This is an important mathematical rule. So these things, or how do you add 0 to another digit and so on, all these rules were worked out in India by very likely the first or third millennium, century, first or third century AD. This was worked out in India. We don't know by whom, but this is the fact. And there is a very interesting story, which some of you would probably know already, but maybe not our younger students here, to illustrate the power of this system. It's a story that comes to us from Persian and Arabic sources in writing, but I have heard it also in Kerala, where there is one Ambalapura temple which has a very similar story, but it is an oral tradition. And the story is very simply that a Brahmin goes to a king, and the name of the Brahmin is given in the Persian sources as Sesa. It's probably a distortion of some Sesha something. And demonstrates to the king, teaches the king the game of chess. And it's a fact that chess also originates in India, by the way. So the king is extremely delighted. And after learning chess, he tells the Brahmin that, tell me what I can give you as a reward. And he expects the Brahmin to mention, so many coins of gold or something. But the Brahmin says, oh, Your Majesty, please give me 1 grain of rice on the first square, and 2 on the second, and 4 on the third, and just keep multiplying by 2. So the king says, is that all you want? And the Brahmin says, I'll be happy with this much. So the Brahmin is dismissed. The king calls his mathematicians, but the story explains this is a kingdom where they still do not have a positional system, decimal-based positional system. So they have some system, and there were many in different parts of India which have been documented epigraphically. The edicts of Ashoka, for example, contain numerals. Those numerals are not in a positional system. They will be equivalent to what, for example, Roman numerals, this kind of principles of non-positional systems. So then you try to do the sum with Roman numbers one evening when you feel very bored. Please take this and start adding these with Roman numbers. And you will see what a headache it becomes. But they were doing it. Romans had a huge bureaucracy. They were keeping accounts. They were doing it with Roman numbers. But it's a tremendous headache. So the next morning, the king finds that they have not gone beyond 8 or 10 squares. So he says, what shall we do? And then one of them says, in the neighboring kingdom, they have just introduced a new system which we are told permits very fast calculation. So they say, okay, let's bring somebody from there. They go, bring a mathematician from the neighboring kingdom who has no difficulty working out, this is a problem, I suppose, for class 9 or 10, I don't know, that the sum of this finite series comes to 2 exponent 64 minus 1. This is the total amount of grains of rice. So the king says, fine, how many bags of rice is that? And then the mathematician tells him, I'm afraid, Your Majesty, that you have been taken for a ride, because if you could sow the entire earth You would have to harvest it 70 times to get this number. So the king says, what shall we do? I'm losing my face in front of this Brahmin now. So the mathematician has a suggestion. He said, why don't you do one thing? Open your granary, send the Brahmin inside, and ask him to start counting and not to stop until he has reached the final number. Which of course will take him many times the age of the universe to come to be, you can calculate easily. If you can count even 10 grains a second, you can just work it out. I mean, it's many times the age of the universe. So this is a very instructive story, and I wish we were using this in our classrooms to explain to to explain the power of this new system of numeral notation which was introduced in India. Shortly after this, we have the appearance of but the date is a little uncertain, of a fascinating manuscript called Bakshali manuscript after a village. The name of a village in northern Pakistan, Bakshali, which was discovered in 1881, unfortunately incomplete, and written in a script which is a cousin script of early Devanagari. It's an early form of Devanagari. It is not exactly Devanagari, and it is in a local Gatha dialect. And this contains, it's actually a kind of fantastic exercise book of mathematics for students. So it has exercises of geometry, fractions, profit and loss, interest, rule of three, summation of series, and so on and so forth. And negative numbers also. And what's unusual about it, it's systematic use of examples. So therefore, certainly custom made for students, and demonstrations, which very often the Siddhantas, which we will see now briefly, are not interested in. The Siddhanta, the main texts, do not give, usually, there are exceptions, step-by-step demonstrations, because it is expected that the student will be able to work out the demonstrations. In fact, Bhaskaracharya, whom we will meet in a few minutes, Bhaskaracharya said once in one of his books, it is the Siddhanta Shiromani, he writes that he gives a result, and then he says, the good student doesn't need any explanation. Full stop. However, for the sake of the dull-headed student, let me explain. You see, this is the idea here. So here, maybe they were addressing themselves to dull-headed students, I don't know. And you see the numerals which they were using, which of course are somewhat close to the numerals which have evolved into all Indian languages. They are all from Brahmi. The Brahmi script is the script which gave all the shape of numerals that we are using today. But we are using them today, returned to us from Europe after traveling through the Arabs, being adopted in the 12th century in Europe, and finally they come back to us. So what we call the Arabic numerals are in fact Indo-Arabic numerals, though we don't use again the word Indian. So this is, and then I'll keep moving on in time. And since we talk about language, because this is all a language-based knowledge tradition, this is one language. Now what is this? Now I will not keep you in suspense, though you might recognize something in the last words, Kala Ardha Jya. Now Jya, for those of you who know, is a word for the chord of the arc. This is the Jya. This is the Jya. And Ardha Jya is, of course, the half chord. What I've put in red. This is a table of sine values of all angles between 0 and 90 degrees, given to us extremely briefly in this language by Aryabhatta. It's a language, you can see the principle here, where basically he gives specific syllables for multiples of 10 and vowels for for the powers of 10 and for the further powers of 10. And this is, interestingly, a non-positional language. It is not an equivalent, as you can see, to our present decimal system. Why was Aryabhatta using this when actually we can prove that he knew the full-fledged decimal system of numeral notation? We can prove it by studying the algorithms which he gives to extract square and cube roots, which are the same algorithms that the senior scholars here would have learned at school at a time when calculators were not used. We were given methods to calculate, to extract square roots. Aryabhatta gives exactly the same. This cannot work with his language. It can work only with the full-fledged decimal system of numeral notation. So why is he using such a system? I propose two reasons. One is that the full-fledged decimal system, probably by that time, had not yet spread to the whole of India. It was just being adopted gradually, region after region. And, he wanted to be understood at large, not to be restricted to one region. The second is mnemonics. Mnemonics means techniques for ease of memorization. And Indians were very good. This is one example. There are many others, which I will not have time to give today, where Indian scholars created techniques that will allow you to memorize things. And this is easy to memorize. Maki, baki, paki, dhaki. You can easily, it's like a song. You can easily memorize this. Whereas memorizing numbers, all the sign values, and they are given here, when you do the conversion, they are all correct to the fourth or fifth decimal. Memorizing all these decimals would be far more difficult. So it is a technique of mnemonic. And why are there, now here there are two more things to be noted. One is the Greeks were very good in trigonometry, but they were only considering the full chord of an angle. If 2 alpha is my angle in green, then the Greeks were always playing with the full chord. But this is a little clumsy and difficult. It was Indians, and possibly Aryabhatta or somebody before him, we don't know, who thought of dividing the chord into two. And what is now this jya, this ardha jya? It is nothing but the sign of alpha if you take the radius as one unit. It's just the sign. So this half chord is your sign. And this is what Indians were very interested in. And the reason for it is astronomical. They were doing astronomy at the same time. I will not have time to describe what they were doing. And in astronomy, when you measure the position of a star or a planet, rising over the horizon, you're immediately going to play with angles because you can't measure the distance so easily, and in fact not at all in those days. So you're purely doing angular measurements, nothing else. And therefore, trigonometry is going to be a crucial ingredient in astronomy in all cultures, all ancient cultures. But Indians were especially good at it. And therefore, once you have angles, you need the signs. And this will be the first sign table used in India. Now, apart from a lot of results that I will not go into, that Aryabhatta gives in his Aryabhatiya, results of geometry, results of algebra, results of arithmetic, he also suddenly has one or two philosophical considerations which are usually not commented upon, but which I find very interesting. One, he says, time is without beginning or end. And I'll come back to it at the end of my talk. This is very striking because we are suddenly plunged in another dimension. The second is that knowing the motion of the earth and the planets on the celestial sphere, one attains the supreme Brahman after piercing through the orbits of the planets and the stars. What exactly is he trying to tell us? Is he trying to tell us that the ultimate objective of astronomy is spiritual, or simply that the contemplation of this vast universe takes you to another dimension which is again spiritual? It's difficult to say. He just drops this remark towards the end of Aryabhatiya and he does not explain. But anyway, it is there and it's interesting to note. Brahmagupta is the next great figure. Well, Varahamihira is there, but Varahamihira is more of a compiler. He's not really a creator. Brahmagupta is a tremendous creator, very self-confident, assertive, aggressive personality, keeps criticizing all his predecessors. He says Aryabhatta knows nothing of mathematics and astronomy. And he disagrees with Aryabhatta in particular because Aryabhatta, incidentally, I should mention at least this much, was propounding the theory that the earth was a sphere hanging in space but revolving on itself, and that this was creating the illusion of rising and setting sun, and that the sun was actually not moving, it was the earth that was rotating. So this was a very brilliant insight. Unfortunately, Varahamihira and Brahmagupta will criticize it very harshly, and they will say that, look, if this was true, a bird leaving its nest early in the morning and coming back in the evening would be unable to find it because the earth will have moved by 180 degrees. So what are you talking about? So it's obvious that the earth is fixed. Actually, the objection is not so trivial. It requires solid physics and understanding of frames of reference and all that to give a complete answer to this question. But unfortunately, Aryabhatta's suggestion will be discarded. However, Brahmagupta, and I may just mention one or two highlights, did a few pioneering breakthroughs in algebra, which Aryabhatta had begun to look into, especially those questions of indeterminate equations, where you are looking for not just any solution, but integral solutions. You want only whole numbers. You want integers. So, and these come as a result of astronomical problems when you consider the number of revolutions of a given planet within a certain era. So these were the kind of problems they were dealing with, and he created this bhavana method. It's a word that means composition, creation, generation. You keep generating solutions through an algorithm. It's an algorithmic method because these kind of equations, like this one, nx2 plus 1 equals y2, if you're looking for integers, you cannot give a formula. There is no formula which gives you straight a solution. It's only an algorithmic method, and his algorithm was extremely efficient. It was rediscovered later in Europe by Euler, but Brahmagupta is 1,100 years before Euler, and Euler called it theorema eximium in Latin, which means a theorem of capital importance. He also proved that once you have one set of solutions, you can work out an infinite set of solutions. And this was rediscovered by the French mathematician Pierre de Fermat in the 17th century, and André Weil, the French mathematician of 20th century, who actually worked in India incidentally. He came to India for some time, and he said, what would have been Fermat's astonishment if some missionary just back from India had told him that his problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. So this is the kind of advances that you find among Indian mathematicians and astronomers, but they are not, unfortunately, they are not well highlighted in our mathematical textbooks. This is about Bhaskaracharya, who was from the 12th century and who lived probably in Maharashtra. And then he took this further, and he's further improved the bhavana method of Brahmagupta. It became known as Chakrawala. And the Chakrawala is, again, chakra because it goes round and round. It's an algorithm. And he will be able to solve solutions like this, which are quite difficult. This comes from a particular astronomical problem. These are the smallest solutions to it. Smallest solutions to it. So you can see that it's not an easy problem. And the first European who will be tackling the same equation is Lagrange, another French mathematician. But it was proved recently by Indian scholars, specifically Dr. M.D. Srinivas, that the Lagrange method was less economical than the Bhaskaracharya algorithm. So it was a little less efficient. And Henkel, German historian of mathematics, will write in the 19th century that this method, Chakravala, is beyond all praise. It is certainly the finest thing achieved in the theory of numbers before Lagrange. So Bhaskaracharya is known for his Leelavati in particular. Leelavati is a brilliant textbook of mathematical exercises where these exercises are put in poetical forms. Bhaskaracharya was a master of Sanskrit poetics. He will use the language with a lot of punning, a lot of multiple meanings, and he will really use this to entertain the students and show them that problems of mathematics, and I will not read them out because I'll be running a little short of time, but these kind of problems can be put in very entertaining form, and most of them are simple. Some of them will take you to quadratic equations, others will deal with questions of interest and compound interest and things like that, and some will be purely geometrical also. And it's quite a delight. I think there are 150 problems also, if I remember well. And this is something that, again, at school level today, we could still use just the same. There's nothing different. The problems are still the same. So this was one of his contributions. Apart from very, very solid mathematics and astronomy, his Leelavati was, you might say, an innovation in pedagogy, in the pedagogy of, how to teach mathematics. And now let me, since we talk about language, let me show you how language was used in certain contexts. For example, the texts of mathematics, the Siddhantas, later on started using numerals, but they always hesitated to use numerals because the numerals were not standardized across India. So numbers were denoted by a series of different systems. Sometimes wholly in word, you can spell out in words a number. Sometimes, like you will be using the Sanskrit here to spell out if you wish. But using one set of names will become again monotonous. So to bring in variety, Indians devised this Bhuta Sankhya, which means basically concrete notation of numbers, where they will associate the concept of zero, emptiness, also identified in India with totality, the concept of oneness, the concept of duality, two, concept of triples, etc., with philosophical or mythological elements of Indian tradition. So, for example, whatever expressed the sky, the totality, would be zero. Whatever expressed uniqueness, you have only one moon, you have only one Atman, one Brahman, one sun, etc., would be one. And it goes on and on. I can't read out the whole thing, but I think you've understood by now. For example, the four yugas, the four ages, the four ashramas of life, the four stages of life, the four Vedas. So if you see ashrama in a text of mathematics, it just means four, nothing else, nothing else. So, and then the four horses of Surya, the Saptarishis, the Saptasagara, etc. And I'll give you just one example from Bhaskaracharya, where he will, this is the word. This is typically the kind of words that you will encounter in texts of mathematics and astronomy. And if you look at it, it's a bit puzzling. It's not something you would expect. So what you have to do is to break it up into its components. And once you have broken it up, then you can attribute the values, because this is sky, atmosphere, ether, void, Yama, of course, is Yama, Rama is Rama, Veda is Veda. And therefore, what are the numbers? All the first are zero. They mean zero. Yama means two. Why does Yama mean two? Because in Rig Veda, Yama comes with Yami, his sister. They are sometimes called the primordial couple. So Yama Yami, it is 2. Rama is 3. Why is Rama 3? Because we have Ramachandra, we have Parashurama, and we have Balarama. We have 3 Ramas. So Rama in mathematics means 3. And Veda means 4, obviously. And you have to reverse the order because in this numeral notation, numbers are reversed, which is perfectly fine. In fact, even in numerals, nothing demands our order. We could have used the opposite order just as well. It would make no difference. So this is, in fact, the number of years in a Kali Yuga. And this was important in Indian astronomy because the start of the Kali Yuga in 3102 BC was taken always as a start of beginning of calculation for the position of the planets and the stars. You may think it is cumbersome, but this is what they did. They were always referring back to this origin point. So this is just an example to show you. Another way to note numbers is, which will be evolved out of Aryabhatta's own system, will be the Katapayadi system worked out in Kerala and which will spread later on to other parts of India, where all the Sanskrit alphabet is basically attributed, the consonants are attributed to a particular number. So you can see, for number 1, any of these will do. For number 2, any of these will do, etc. And if you want 0, take a standalone vowel, keep a vowel separate. That will mean 0. Any vowel. And finally, other vowels, you can just add to the consonant as you wish. What is the advantage of this system is that you have great flexibility. And therefore, if you have a number, you choose whatever you wish, which will give a meaning to what you compose in Sanskrit. You should, because you should be good in Sanskrit, therefore you can give meaning. And I have even today a friend in Kerala. He is a Vedic scholar and also was a professor of English and physics and so on, and a poet. And he was trained when he was youngster in Katapayadi. So all the telephone numbers of his friends, he will not write them down or he will not keep them in a cell phone. He keeps them here in Katapayadi. So he translates. Any phone number of yours can become a Sanskrit shloka with meaning. It may be, for example, you know, the garden blooming with flowers, anything. And all you have to do is associate your friend with this particular meaning which you have composed. And this is the beauty of the system. So, for example, we will find by Shankara Varman, who will be a 18th century mathematician, one of the last in the Kerala school, we find this Badram Buddhi Siddha Janma Ganita Shraddha Smayad Bupagihi. And if you so this is something which is, you know, easy from the point of view of mnemonics. You can easily remember that. Now you translate by this system into all these numbers and you take it backward and, you take it backward and this is pi, 3.141592, etc. Correct 17 decimals of pi, which had been calculated by methods worked out by Madhava, the initiator of the Kerala school. It's impossible to deal with his contributions, who for the first time, this was a very major breakthrough in the history of mathematics, worked out infinite series for the trigonometric functions, and therefore this leads you immediately to an infinite expansion for pi, and then worked out all kinds of methods of fast converging series to calculate as many decimals as you want. This was done in the Kerala School of Mathematics, and of course reinvented by Newton and Leibniz and Gregory, who also worked out the same series a couple of centuries later in Europe. Once again, and I'm sorry if I repeat myself, when we teach those series of expansions of sines and arctangent and cosine to our students, we call them the Newton series, Leibniz series, and Gregory series. Even now in the West, they are sometimes called Madhava Leibniz series, Madhava Gregory series, but in India we don't do it. There's something wrong with us. I don't know what. Another example, Narayana Bhattadri, who was one of the minor mathematicians of the Kerala school, ends a whole text, he ends it with this shloka. He says, Ayur Arogya Sokyam, which means basically that he wishes us Ayur, long life, Arogya, good health, and Sokyam, that is to say happiness. So you think he's just telling you, giving some kind of blessing to his reader? Not at all. It is a number in Katapayadi, which is this number. And when you count it, as I said, from the beginning of the start of the Kali Yuga in 3102 BC, it takes you in Malayalam era to 8th December 1586, which is the day on which he concludes the writing of his book. And this is how the days were often indicated in the Kerala school. So now, and incidentally, as a side remark, and here there would be a lot to say about, but I cannot deal with everything, about the interaction between mathematics and other disciplines in India. In music especially, lots of techniques were evolved from mathematical perspectives to work out a lot of things connected with the notes of music, the notations, and the notation of the ragas in Carnatic music. The ragas all are associated to a certain number and sequence of swaras, as you know. The sequence of swara is what determines the raga. To denote this, it was translated into Katapayadi, and even today, good Carnatic musicians will learn the ragas by their name in Katapayadi, and that can be mentally translated back into numbers. And so this is just to show you the interplay. These knowledge traditions are never isolated. They keep interacting. There would be a lot to say about this. Use of Sanskrit. Now we come to a few last points, especially problems of terminology. Sanskrit has given immensely rich wealth of technical terms in Indian science. And you have terms in mathematics, astronomy, of course, in metallurgy, in chemistry, like here, in all branches, basically, in agriculture, in water conservation, in everything. And the problem is that sometimes we are not very sure what those terms mean because they're not explained, they are taken to be understood. So I'm giving you a single example from Indian chemistry. There's a big chemical tradition. Prafulla Chandra Roy in the early 20th century was the first to write a massive history of Hindu chemistry. He was a very eminent chemist himself. And in the text, there are many things which are surprising, difficult to understand, and which would require a lot of work by our chemists to figure out and to either validate or maybe invalidate if need be, whatever it may be. And these are, for example, the problems, and I'm not going to read out these names, you can have a look, of how do you purify mercury? Not purify, prepare it for human consumption. Mercury is a poison. Yet, Ayurveda and other medicines like Siddha medicine in South India have used it and are still using it in medical preparations for patients. And they will give you mercury prepared through a certain number of, whether this is exactly the same or not, I do not know. But these texts list out all these techniques to finally make mercury fit for internal use after combining it with a number of plants and possibly metals. But we do not really understand what these steps imply. They're not explained. So this is to show you one of the problems that we encounter in Indian texts. And even the apparatus, even the equipment are described in the text, but it's not always very, very sure. We're not always very sure what kind of operations they were used to. These are fairly simple, and these yantras, they are called, were used certainly for processes of distillation, sublimation, condensation, and so on, but fumigation also. But sometimes there are many more, and it's not very clear what they were doing with this apparatus. So I'm showing this simply to show that there is a huge potential field of research. Now, I want to end my talk. Now, I'll take another 5 minutes or so with some thoughts on how this Indian scientific mind was working. And it was working in a way which was fairly different from the Chinese scientific mind or the Greek scientific mind. Every of these cultures had its own specific approaches. Now, first of all, I want to simply point out that there's been an accusation made against Indian science that it was elitist. It was restricted to a small class of scholars and so on. This is actually not true, because even though there may have been a small class of scholars creating the scholarship, it was always busy interacting with what has been known as Loka Parampara, the popular traditions. Especially, it's very visible, even mathematics, calculation techniques were adopted by people at large in all occupations of life. Then astronomy was of great use at the popular level for astrological calculations, for the making of the panchangas and so on. And then in medicine in particular, you have a great interface between a theoretical system which is Ayurveda and local health traditions of documenting herbal formulas and so on. So this interplay is very visible, and even in architecture also, where you have a theory of architecture, Vastu Shastra, Shilpi Shastra, and you have also the practitioners. And the practitioners always belong to the lower classes of the society. So this dialogue is going on, and therefore there is no isolation, ivory tower phenomenon of Indian science. Secondly, I have already alluded to this. I'll briefly mention that the Greeks are those who pioneered the axiomatic method of doing science. If you read Euclid, the Elements, you start from axioms. Axioms are taken as granted, and you build upon the axioms. By logic, you create your theorems. Indians never followed this approach. They were not interested in axiomatics. They would go directly to results. They would be interested in finding good results that worked, and they were excellent at working out algorithms for the purpose. And therefore, it's a kind of very pragmatic approach to science. However, I should mention here that the popular notion that Indians didn't have the concept of proof is wrong. There was a concept of proof. It was called sometimes yukti, sometimes upapati. And this proof was more in terms of a logical step-by-step reasoning leading you to the result or the formula. And it was not exactly a proof in the Greek sense of the term, but it did take you logically through all the steps in the reasoning. So there is something at least in this notion of proof. The Indians encouraged dialogue through this tradition of commentaries, which I have referred to. So it is something which is a little unlike what you see in medieval Europe, for example, where there was no perfect intellectual freedom. We know what happened to Galileo when he tried to promote the heliocentric system. He was told that his life was in danger and he had to officially recant it. Now, this never happened in India. There was never any, actually disagreement was always readily accepted. And there was free discussion and dissent, if need be, among these scholars. So, its accomplishment need to be studied for a proper assessment of Indian civilization. And then, of course, there are problems of interpretation, and I will end with this. I'll take just a few minutes, where there are cases where we have to be honest, and we can't always know what happens. For example, take this mantra of the Rig Veda here at the top, which is a very, very ordinary mantra to Surya. There's nothing special about it. However, Sayana, who is a 15th century commentator on the Rig Veda in the Vijayanagar Empire, and who produced a monumental commentary on the Rig Veda, produces this comment here. Thus it is remembered, you Surya, who traverse 2,202 yojanas in half a nimesha. What is a yojana? It is, in this time, 8,000 human heights. 8,000 human heights. It's a unit of length, a long unit of length. So it works out to about 13.6 kilometers, and the nimesha has been calculated to be 16/75th of a second precisely. When you work it out, you get this much, and it happens to be very close to the speed of light. Now this creates a problem for us, because the sun doesn't move at this speed, and astronomers knew it. Indian astronomers knew that the sun was moving at a certain speed, or in relative terms to the earth, but not a speed like this. And this never happens, this is never mentioned in the Siddhantic literature, Aryabhata, Brahmagupta, Bhaskaracharya, and so on. So what is he trying to say? We don't have an explanation. Is it that they knew the speed of light? But this is in the pre-telescopic era, and the speed of light was first measured with a telescope, measuring variations in the orbits of the moons of Jupiter by Romer in the 17th century in Europe. So without a telescope, normally, as far as we know, you can't measure the speed of light. So what exactly is he trying to say? So some people say, well, it's just a coincidence. But why should he be so specific? You know, sahasre dve sate dve yojane. Why this precision? We have no answer. So let us just leave it as a question. People rush to say that, you know, we knew the speed of light. Well, I would like to have some confirmation elsewhere before we can make such a statement. Let us leave it as an open question. Then, the riddle of invisible corpuscles, and this is very clear now. Mahabharata, I won't read out this to save time, has a passage where ahimsa is severely criticized because the very fact of our breathing destroys a lot of living organisms, whether the earth and the air swarm with living organisms. How do they know that the air swarms with living organisms? And it becomes even much clearer in the Ashtanga Hridaya Samhita, which is one of the fundamental texts of Ayurveda, a few centuries AD, which describes blood corpuscles in the blood, and this is an exact quotation. It says there are corpuscles in the blood which are circular, legless, invisible, and coppery in color. And this is an almost perfect description of the red blood corpuscles. How do they know? This is too much of a coincidence. Now, when we, you know, I said that the Indians are fascinated by very, very large numbers, the infinity of time, the infinity of numbers, but they are also fascinated by the infinitesimal. So, for example, this paramanu, this atom, is described in a number of texts and taken to be the fundamental unit of matter as a concept. But the dimension is given here by Brahmagupta, and when you work it out, it comes to 70 nanometers. Now, it's still far too big for an atom, but nevertheless, why should they be considering such tiny, invisible dimensions? We can't really answer. Weight units also, the Dvamshi in Ayurveda is about 1/10 of a milligram. There would be no use for such a unit. If you take the time, Bhaskaracharya defines all units of time starting from the Truti. And the Truti is what? It is this much. You can read it out and save me the trouble of reading it out. And it works out to 30 microseconds. Or you have units of angles. Indians used the degree, 360 degrees, among other units. They divided the degree into 60, so that's the minute, and that minute was divided into 60, so that is the second of an angle. But why stop there? They continued, They divided the second into 60 and that also further into 60, which would be of no use whatsoever. So here we find a desire to at least conceptually explore dimensions. And we find the application in the question of time in particular, where you have here on the left, and again I won't read out, you can understand, these are the traditional Puranic units of time which you find also in Mahabharata. And this leads you to a day of Brahma, which is 4.32 billion years. Okay? Now you might say useless, no use at all. But if you add it to a night of Brahma, then you get 8.64 billion. Now I'm coming back to that in a second. Meantime, these are the units of time, cosmic time, which were being considered in the West, especially by, derived from the Bible. So either by the universe was created on this date according to Jewish scholars, and this date according to Christian scholars, all the way to the 19th century. It is only Darwinian evolution which disposed of those dates. So Carl Sagan, the author of Cosmos, some of you would be familiar with his name. He was a great Indian astronomer, did a lot of popularization of astronomy also. And in his book Cosmos, he writes that Hinduism is the only religion in which the time scales correspond, no doubt by accident. He attributes it to accident, and quite possibly it may be an accident, but correspond to those of modern scientific cosmology, because the age of the universe considered today is about 13 billion years. And the day and night of Brahma comes to 8.6. So it's the same order of magnitude. How come? And he says there are still longer scales of time. So let me finish, and I'll close now by listing a few of these accidents. So first of all, this one, which Carl Sagan was commenting upon, then the notion that space is without limit. This was Bhaskara the First, who specifically mentioned that no limit to space, no limit to time also according to Aryabhatta. Concept of microorganisms and blood corpuscles, which is really very difficult to explain because they didn't have microscopes in those days. The concept of the Dashavatar. Now, very briefly, you know that according to Vaishnava traditions, Lord Vishnu took birth first of all as a fish, Matsya Avatar, then as a tortoise, Kurma Avatar, then as a wild boar, and finally as a half animal, half man, which is Narasimha, and then as a dwarf man, etc. Now, the fish is a fish, the tortoise is a reptile, the wild boar is a mammal, then you have Narasimha, half animal, half man, then you have a dwarf man, and then you have men with various stages of evolution. So it is certainly a picture of evolution at a certain notional level. It is not Darwinian evolution. Again, people rush to conclusion and to claims, and they say, see, we knew all about Darwinian evolution back then. No, of course not. This is not Darwinian evolution, but it seems to be a kind of intuition of the evolution of physical bodies. And I will end with this one. There are Jaina texts. Jains were excellent at counting things. They were obsessed with it. Professor Jain can give you a talk one day on this. You should actually invite him to give you a talk at counting stuff. And they counted species living on Earth. All species, all of them, on Earth, in the sea, whatever. And they give in Jain text this number, 8.4 million species. Now again, you might say it's ridiculous. It's conceptual. And it so happens that by accident, 4 years ago, there was a paper in PLOS Biology which tried to count species now from a scientific angle, and they came to the number of 8.7 million, plus or minus 1 million. They're not very, plus or minus 1 million. So how come that it so happens that these colossal numbers, which sometimes were ridiculed by European scholars in the 19th century, those huge scales of time and so on, how come that it all kind of coincides with the concept of the universe we have today? So I will end with this question. I will not try to answer it. In fact, I have no answer to give. Or maybe I do have, but anyway, it's better to leave it as a question mark. And I'm sorry, I think I took a little more time. I had a couple more slides, but this is a good way of ending the talk. And I will simply say in conclusion that the field is immensely rich. And we have no excuse for not exploring it. And if any of you wish, through the Sanskrit Club and Professor Anil in particular, I have been, giving some references of very genuine material. Genuine means solid, well-researched academic value, and so on. And be careful, because if you go to the net, and today our students, have this impulse of immediately rushing to the net, you will find a lot of spurious material, non-genuine, wild claims, or misunderstood concept, misunderstood, half-digested material. So it is better to go to the real, genuine sources, and I'm sure you would find it very, very rewarding. And it's not a matter of beating our chest that we Indians were superior to the Europeans and we did it all centuries ahead of that. It doesn't matter. What matters is simply to have a realistic, genuine estimate of what was achieved here, because then only can it give us a proper perspective of Indian civilization and all its accomplishments in all fields of knowledge. Thank you very much.